Hello, and welcome to Linear Algebra. This is lecture 28, Normed Spaces. Okay, so last time we talked about least squares. So this was about how we could use orthogonal projections to solve optimization problems. This time, we want to talk about how to measure the size of a linear map. Okay, so sometimes it is useful to study vectors in spaces with norms. Right? So of course, if you have an inner product, then you have a norm. But there are some norms that don't come from an inner product. Okay, so first, let's agree on exactly what we mean by a norm when we don't have an inner product, and then we'll see some examples. So let's let V be a vector space over field F, and we are continuing with the convention that F is either the real numbers or the complex numbers. Then a norm on V is a real valued function right, which will denote the usual way, such that, okay, here's what we're going to require. It's going to be non-negative. Right, so the norm of a vector is greater than or equal to 0 for any vector in V. It's going to be definite, which means that if the norm of a vector is 0, then that vector is the 0 vector. We're going to require positive homogeneity. Right, so if you multiply a vector by a scalar, the norm gets changed by multiplying by the modulus of the scalar. And then finally, we're going to require the triangle inequality. Right, so remember this says that the norm of a sum of two vectors is bounded above by the sum of the norms. Okay, so of course, our first example, and I'll just put it here as a remark, if a norm comes from an inner product, right, so the norm of a vector is equal to square root of the inner product of the vector with itself, then it is a norm. In the sense of this definition. Okay, so the things we've been calling norms, they are norms with respect to this definition, which you had better be, or else we were defining things wrong. Okay, and then here are our first couple of examples. These we're going to show in a little while do not come from an inner product, but you'll see they're very natural ways of measuring the size. So first, the L1 norm. on Cn. So if you give me a vector in Cn, then I'll denote this like this, L1 norm. You just take the sum of the entries, take the modulus of each entry, and then sum those together. That's a very good measure of the size of the vector, right? And of course, here we have the L1 norm. Previously, we've talked about the little L2 norm. You can imagine that if you little LP, the little LP norm, you would put a pth power here and a pth power for each of these. And that also will give you a norm. Here's another example. The L infinity norm. On continuous functions on 0, 1, say with values in the complex numbers. So the L infinity norm of a function is to take the maximum of all of the moduli of the values of the function. Right? So you have a continuous function on a closed and bounded interval, so it achieves its maximum. So there is some point where this maximum will be achieved. In general, you would put a soup here if you're not necessarily working with continuous functions, or you're working on a non-compact set. Okay, so as I mentioned, we're going to prove in a moment that neither of these comes from an inner product. How can we possibly know that? Well, here's the thing. If a norm comes from an inner product, it satisfies the parallelogram law. Right, so the parallelogram law says that the norm, so for any two vectors, the norm of v plus w squared plus the norm of v minus w squared is equal to 2 times the norm of v squared plus the norm of w squared. Right, and the reason it's called the parallelogram law is that if you have a vector v and a vector w, right, so let me draw v and w again. So then this vector would be v plus w. This vector would be v minus w, point like that. And so here, what I have is the sum of the squares of the diagonals are equal to the sum of the squares of the sides of the parallelogram. Right, so hence the name. Right, okay, so every norm that comes from an inner product satisfies the parallelogram law, and then the converse is also true. If a norm satisfies the parallelogram law, then it comes from an inner product. For example, if the field is the real numbers, then you can define the inner product of two vectors to be 1/2 the norm of v plus w squared minus norm of v squared minus norm of w squared. Okay, so the claim is that if you're working with the real numbers and you're given a norm that satisfies the parallelogram law, then you can use this formula to define the inner product between any two vectors. And this will satisfy the definition of inner product that we talked about a few classes ago. So I'll leave that as an exercise. Go ahead and check that this satisfies all of the properties you want from an inner product. So it should be linear in the first variable, for example. It should be conjugate linear, which over the real number, conjugate symmetric, which over the real numbers means symmetric. So this doesn't change if we change the order of v and w. That's obvious. And so on. So check that all of those properties hold. If you're working with the complex numbers, it's also true that if you have a norm that satisfies the parallelogram law, it comes from a inner product. And the formula for the inner product is similar, but a little longer because you have to worry about complex numbers, of course. So the formula is in the exercises of the book, and it's also a simple exercise to check that it gives you an inner product. Great, so now we have a way of checking, given a norm, does it come from an inner product? So let's check these two examples. Right, and well, I've already spoiled the answer. So I'll just say here, note that the L1 norm on Cn does not satisfy the parallelogram law. So to check that a norm doesn't satisfy the parallelogram law, since it's supposed to hold for all vectors v and w, it's enough to just exhibit a pair v and w that does not satisfy this equality. So for the little L1 norm, you could, for example, use the vectors v given by 1, 1, and w given by 1, minus 1. On C squared. Right? So I'll let you do the check, but just plug these in to this side using the little L1 norm, and plug them into this side using the little L1 norm, and check that you get different things. And that the L infinity norm on the continuous functions on 0, 1 with complex values doesn't either. So here, I'll also let you work out the details, but here are functions you could try. So consider an f that does something like this. So let's say its maximum is 1, and it's achieved over here on the left side of the 0, 1 interval. And let's have a function g whose graph looks like this. So it also has its maximum of 1, but that's achieved over here where f is 0 and g be 0 everywhere where f is not 0. So I will let you plug these functions into the left-hand side and into the right-hand side and check that you get different things. Okay, great. So that shows that looking at norm spaces gives us a strictly larger class of norms than when we were looking at inner product spaces. And I hope you will agree that the little L1 norm and the L infinity norm are very natural ways of measuring length of a vector, so that this was a useful generalization. Of course, we'll see another reason why we did that, why we do this generalization in a moment. But before we do, let me point out that the triangle inequality implies something that looks slightly different, but is really the same. So remark, on any normed space, we have the following. So you could ask, well, the triangle inequality is about sum of vectors. Can you say anything about the difference of vectors? And what you can say is that this is bounded below by the difference of the lengths, right, in absolute value. Okay, so why is this true? Well, indeed. This is equivalent to saying that the maximum of norm of V minus norm of W and norm of W minus norm of V is bounded above by the norm of V minus W. So we'll just show that both of these are bounded above by this, and then we're done. So let's look at the first one, norm of V minus norm of W. We want to say that this is bounded above by the norm of V minus norm of W, sorry, by the norm of V minus W, but that's equivalent to saying that the norm of V is bounded above by norm of V minus W plus the norm of W. Now notice that this is the triangle inequality if you start with this vector and this vector, right? Because triangle inequality says that the norm of the sum of this guy and this guy, which is this, is bounded above by the sum of the norm of this guy and the norm of this guy. So we're all set. And similarly, if we had started with these norms in the opposite order, we want to show this is bounded above by the norm of V minus W. Well, that's equivalent to having the norm of W bounded above by norm of V minus W plus the norm of V. And now all we're going to do is we're going to write the norm of V minus W as the norm of W minus V. And now we're right back where we were right here. So that's also true. Okay, so that means that we've established on any normed space, we have this sort of reverse triangle inequality. Okay, so I make that remark because I'm going to use that in the next proof. So keep that in mind. But before we get to another proof, here is a definition. Well, not quite yet. We're working up to the definition. So if V and W are inner product spaces, right? So for this course, our main interest is in inner product spaces. We will define a norm on the linear maps between V and W. Called the operator norm. Okay, so our main subject of interest are inner product spaces. But when we're studying inner product spaces, we also want to understand the linear maps between inner product spaces. And to talk about the size of a map between these spaces, we will introduce an operator norm, something that doesn't come from an inner product. And that's why we're talking about norms. As a first step, we will show that for any linear map between V and W, the function that takes a vector and gives you back a real number, f of V is equal to the length of T of V, is continuous. Okay, so we'll show this in a very explicit way. Here's the lemma. Let V and W be finite dimensional. Inner product spaces and let T be a linear map between V and W. So here and often, we're going to assume that vector spaces are finite dimensional if it makes our life simpler. There's a lot you can do for infinite dimensional inner product spaces, but that just brings in complications that we're not going to talk about this semester. I highly recommend taking a functional analysis course if you're interested in what happens in infinite dimensions. Okay, but let's say you're working with finite dimensional inner product spaces and you have a linear map. Then there is a constant C positive such that for any V, W in the vector space V, we have, so the size of T of V minus the size of T of W in modulus for absolute value is bounded above by the size of T of V minus T of W, and that in turn is bounded above by C times the size of V minus W. Right? It's this last part that gives us continuity. Okay, proof. So first, the first inequality is immediate. From the remark. Right. So this is just the reverse triangle inequality and it doesn't use anything. For the second inequality, let's start by picking F1 through Fn an orthonormal basis. Of V. Then for any vector, call it U in V, we have, okay, let's compute the norm of T of U. Okay, because we have an orthonormal basis, we know exactly how to write U in terms of that basis, right? So it's a basis, so every vector is a linear combination of the elements of the basis, but because it's orthonormal, we also know exactly what the coefficients are, right? It's just the inner product of U with Fj. That's the coefficient of Fj in this linear combination, right? So the size of T of U is equal to the size of T of this linear combination. And then we can write that as, because T is linear, I can pull out the sum j goes from 1 to n. And let's go ahead and pull out the coefficient as well. Inner product of U with Fj, and then T of Fj. Okay, next let's use the triangle inequality to say that this is bounded above by the sum j goes from 1 to n of the size of each of these terms. And then let's use positive homogeneity to pull out the coefficient from the norm. Okay, next I want to use the Cauchy-Schwarz inequality, right? So we have an inner product space, and so we have the Cauchy-Schwarz inequality. So this is bounded above each of these inner products is bounded above by the product of the lengths and the size of fj is equal to 1 because I picked an orthonormal basis. The size of u, well, that's a common factor. I could pull that out. So this is equal to the norm of u times the sum j goes from 1 to n of the size of t of fj. Okay, so let's call this C, right? That's our number C. With C equal to this number, sum j goes from 1 to n of the norm of t of fj, we have that the size of t of u is bounded above by this constant times the size of u for every u in the vector space. Okay, in particular, the size of t of v minus t of w, well, that's equal to the size of t of v minus w. And so it's bounded above by this constant times the size of v minus w. And that is what we wanted to check. Okay, so wonderful. So the function that assigns to each vector the size of t of that vector is a continuous function. So in particular, if we look at it on those vectors of of unit length, then we're going to find a maximum. So here's the lemma. Let VW be finite dimensional. Inner product spaces. And let T be a linear map between them. There is a unit vector, call it U, inside V, such that the norm of T of V is bounded above by the norm of T of U whenever the vector V has size of V equal to 1. Right? So I'm just looking at the size of T of V when V is a unit vector. And I'm just stating here that there is a unit vector where that size is largest. Okay, and the proof is just to say that the set of the unit vectors is a closed and bounded subset of V. The function f that we just talked about from V to the real numbers that assigns to a real number the size of T of V is continuous. So it achieves a maximum on this set, right? And U is just where that maximum is achieved. Okay, so with those preliminary lemmas out of the way, we can now define the size of a linear map. Let V and W be finite dimensional. Inner product spaces. And let T be a linear map between them. The operator norm of T, which we'll denote by norm of T sub up, is just this maximum value. So it's going to be the maximum over all the vectors in V whose length is 1 of the size of T of V. Okay, so notice for any V and V not equal to 0, we have the norm of T of V is, okay, well, because V is not the 0 vector, I can write V as norm of V times V divided by the norm of V. And then I can use that T is linear and that the norm is positive homogeneous to write this as norm of V times the norm of T of V divided by norm of V. Now, this is a unit vector. Regardless of what the norm of V is, this has norm 1. So this is bounded above by the operator norm of T times the norm of V. Okay, so there we go. We've proven this inequality for any non-zero vector. Of course, if the vector is the 0 vector, then this is equal to 0 and this is equal to 0. So you also have this inequality for the 0 vector. So in fact, the norm of T of V is bounded above by the operator norm of T times the norm of V for every vector V. Okay, so even though we used unit vectors to define the operator norm, the inequality you get works for all vectors. Okay, now we should really justify calling it the operator norm. So we'll state that as a theorem. The operator norm is a norm on the vector space of linear maps between V and W. Okay, great. So proof. So we need to show that it is non-negative. Right, so here, let me, instead of flipping back and forth, let me go ahead and write the operator norm definition right here so we can refer to it more easily. So this is the maximum among all of the vectors in V of unit length of the size of T of V. Okay, so this is clearly non-negative, right? Because you're taking the maximum of a bunch of non-negative numbers. It's also clearly definite, right? So if the operator norm of T is equal to 0, then, well, if the maximum of these non-negative numbers is 0, that means that all of these non-negative numbers are actually 0. So this is the same as saying T of V is equal to 0 for all V of unit vectors. But if a linear map is equal to 0 on all unit vectors, then t is just identically equal to 0. So it is definite. Next, let's check positive homogeneous. Positive homogeneous. Okay, so given a linear map and a scalar a, the norm of a times t is equal to the maximum among the unit vectors of the size of a times t applied to the vector v. Okay. But the norm here, this is the norm in W that we're using, and it is positive homogeneous. So I can pull the A out in modulus. Okay, and now if you're looking at the maximum of A times a bunch of numbers, that's the same as A times the maximum of those numbers, because everybody inside is not negative. So I can write this as modulus of A times the maximum among all unit vectors of the norm of t of v. But of course, that's just modulus of A times the operator norm of t. Great. So that's positive homogeneous. And so the only thing left to check is the triangle inequality. Okay. So let's say we're given two linear maps between B and W, and we want to look at the norm of S plus T. Okay, well, the operator norm of S plus T, by definition, this is the maximum among all unit vectors in V of the size of S plus T applied to V. Okay, that is the maximum among all unit vectors in V of the size of S of V plus T of V. Okay, now we can use the triangle inequality inside W to see that that's bounded above by the maximum among unit vectors of the size of S of V plus the size of T of V. Okay, now we're going to use what we talked about right before stating the theorem to bound each of these by operator norm of S times norm of V plus operator norm of T times the norm of V. Okay, now I have a common factor of the norm of V, and just like we did over here, we can pull that out of the maximum because everybody in sight is non-negative. In fact, we don't even have to do that. Let's just stare at this. I'm taking the maximum. Norm of V is equal to 1. So this is just equal to 1, and this is just equal to 1. And then I'm left with the operator norm of S plus the operator norm of T, which doesn't depend on the vector. So this is just equal on the nose with operator norm of S plus operator norm of T. And that's triangle inequality. We start with the operator norm of S plus T, and then we see that it is less than or equal to the operator norm of S plus the operator norm of T. So we are all set. The operator norm is a norm. Okay, as usual, when we define something for a linear map, there is an analogous definition for a matrix, which is basically the same thing, just specialized to the case where the vector spaces V and W are just powers of the field. But let's go ahead and spell this out. So we can similarly define the operator norm of a matrix if A is an m by n matrix with coefficients in F, then the operator norm of A is going to be the max among all of the vectors in Fn with unit length of the size of A times X. Okay. One use of the operator norm, usually in this matrix form, is to estimate the effect of a measurement error. Okay, so assume, say that A is invertible. We're given a vector B and we're interested in the solution to AX equal to B. Okay, so i.e., we're looking for the vector X, which is given by A inverse times B. Now, in real life, say, the vector you're given will have some measurement error. So what you're actually given is, let's call it B hat. So this would be B plus H, right, where H is the error. So then if everything with solving the system goes well, then the X we find is actually A inverse of B hat. So A inverse of B plus H. And this obviously differs from the correct answer by A inverse times H. So the size of this error is, well, the norm of A inverse times H, which is bounded above by the operator norm of A inverse times the size of H. Okay, now, since the operator norm is defined as a maximum, right, there is some direction in which this would actually be an equality. Right, so this is telling us, like, the worst case scenario, how much does this error in B affect the error in X? Right, so it can happen that you have a matrix A that is invertible, but maybe it's close to being singular. It's close to not having an inverse. Right, so what does close to being singular mean? Well, for example, we know that a matrix that has an eigenvalue 0 is not injective, right? And if you have a square matrix over the complex numbers, then it's going to be, if you have a diagonalizable matrix, let's say for simplicity, then it's going to be invertible as long as 0 is not an eigenvalue. Well, what if you have a very small eigenvalue, right? Let's say you have 0.00001 as an eigenvalue. Well, then you're very close to being to not being invertible. And when you're doing computations on computers, there's rounding errors. And what if you have an eigenvalue that's smaller than the rounding error? Then the computer can't really tell that you're invertible. What if it's close to the rounding error? So this is where you would notice that. So the size of A inverse is going to be very large if A is close to being singular. And this tells you that the effect is that if you have a matrix that's close to being singular, it's going to be exaggerating the effect of a measurement error, right? You're going to have very precise measurements of B in order to get any sort of reasonable answer when you, reasonable approximation to X when you compute A inverse times B hat. So anyway, the operator norm is a very useful thing in numerical questions related to linear algebra. Okay, so that's where we'll stop the lecture. Feel free to stop listening now. I'll just talk a little longer and tell you some historical context. So one name that's come up recently was Frobenius, for the Frobenius norm and the Frobenius inner product of matrices. And we're going to talk more about the Frobenius norm later when we're talking about things like singular value decompositions. So I thought I'd tell you a little bit about him. So this is Ferdinand Georg Frobenius, who lived from 1849 to 1917 in Germany. So you'll notice those are very interesting times in Germany. So he was a German mathematician who made many important contributions, especially to abstract algebra. He worked on theory of groups. So group is a set with a single operation. So we've seen many of these. We've seen fields, we've seen vector spaces, for example. Both of those have two operations, addition and multiplication. The group is a set with one operation. So in both of these examples, if you look at the additive structure and just forget the multiplication, you get a group. A special kind of group, it's a Abelian because it's commutative. Abelian, of course, named after Abel. But in general, it's just a set with an associative operation that has an identity and inverses. The set of invertible matrices is another example of a group, one that's not Abelian. One of Frobenius's contributions was to point out that a valuable tool for understanding a group is to look at the structure-preserving maps into the complex numbers. This is actually a really useful thing beyond just looking at groups. If you look at a vector space, which of course the additive part is a group, but if you look at a vector space, it tells you that an interesting thing to look at is the vector space of all linear maps from the vector space to the underlying field. So if you're working with the complex numbers, all linear maps from your vector space to the complex numbers, or similarly, if you're working with the real numbers, or with any finite field, for example. That is important enough, it gets a name. It's called the dual vector space. And it's a really useful thing, especially if you look at functional analysis. Dual vector spaces show up a lot. It's denoted by V star. So just like the adjoint of linear map gets a star, and that is not a coincidence. Frobenius's papers, it's been pointed out, often read like present day textbooks, which tells you how influential they were, that's still how we present the topic. Frobenius studied in Berlin under Weierstrass. Weierstrass himself, of course, is very famous, and one of the things he's famous for is for being a fantastic mathematical advisor, which you can gauge by just how many of his students went on to have important careers. This included, for example, Sofia Kovalevskaya, who Weierstrass taught privately because as a woman, she was not allowed in the University of Berlin. But Weierstrass had a very high opinion of her and arranged for her to get an honorary PhD from the University of Göttingen, and then helped her get a position in Stockholm. Another of Weierstrass's students was Felix Klein, who was something like Frobenius's nemesis. They ended up running rival math departments. Frobenius was in Berlin, and Klein was in Göttingen. And Frobenius watched with great annoyance as Göttingen won the competition. Right, so Berlin was a great center of mathematics when Frobenius studied there, for example, but Göttingen overtook it in importance by the time of Frobenius's death. And Göttingen would be the premier place for mathematics in the world until World War II, and the restrictions on Jewish mathematicians forced a great part of its members to flee the country. So why did Göttingen win out over Berlin? Well, some of it is ascribed to Frobenius's personality. It seems he was very quarrelsome and hard to get along with, very rigid in his points of view. But mostly it's because Frobenius and other professors at Berlin, it's not just him, but certainly he thought that what they should be concerned with was pure abstract math, not polluted with applications. And if there were applications, then that should be studied in some sort of technical school. Whereas in Göttingen, they were very interested in applications of math and studying applied math. It would probably have annoyed Frobenius that shortly after his death, if he had lived into the 20s and the 30s, he would have seen his very abstract and pure math become an important tool in physics, where it was used to answer group theory questions that came up in quantum mechanics. All right, we'll stop there and pick it up from there next time.